Hey everyone, and welcome. Today, we are pulling back the curtain on one of the most fundamental concepts in all of computing, something that's happening thousands of times a second inside your device right now. We're talking about interrupts, the true unsung heroes that make modern multitasking possible. Have you ever stopped to wonder how your computer can be streaming music, tracking your mouse movements, and downloading a file all at the same time? It really feels like magic, but it's not. It's all thanks to an incredibly clever system for managing a processor's attention. Okay, to really wrap our heads around this, let's use an analogy. I want you to picture your computer's CPU as a master chef. This chef is in the zone, working on a very complicated main course, following the recipe step by step with total focus. That recipe? That's your main program.
So what happens when things pop up that aren't part of that main recipe? This is the central problem that every single processor has to solve.
For our chef, maybe an oven timer goes off or a delivery person rings the doorbell. For a CPU, these are things like you pressing a key, moving your mouse, or a new chunk of data arriving from the network. These are all external events that demand attention, right now.
Now, there are a couple of ways to deal with this. Let's start with the first and, well, let's just call it the inefficient way. It's a technique called polling.
With polling, our chef would have to constantly stop what they're doing. So stop chopping vegetables, look over at the oven timer, check if it's done, then go back to chopping. A second later, check again and again. You can see how this would be unbelievably distracting and just slow everything down.
Yeah, this constant checking is so wasteful. It ties the CPU down in this useless loop, asking, are we there yet? Are we there yet? There has to be a better way, right? An event-driven method that lets the CPU focus until something actually needs its attention.
And that brings us to the much more elegant solution, the hero of our story today, the interrupt.
So instead of constantly checking, what if the timer just made a loud ding when the food was ready? The chef hears the signal, calmly puts down their knife, deals with the oven, and then, and this is the absolute key, returns to chopping vegetables at the exact spot they left off, without missing a beat. That ding, that's an interrupt.
Okay, so that's the what. It's an efficient signal. But how does a processor actually pull this off? Let's dive into the mechanics.
When an interrupt happens, the CPU doesn't just guess what to do. Nope, it runs a special pre-written piece of code called an interrupt service routine, or ISR for short. You can think of it as a little mini recipe in the back of the cookbook, just for handling the oven timer.
The whole process breaks down into 4 really important steps. A device sends a signal, the CPU saves what it's doing, it runs that special ISR code, and then it goes right back to its original job. Let's walk through it. Okay, first up, a device, like your keyboard or that timer, sends an electrical signal, an INT or interrupt request, straight to the processor. The timer has officially dinged.
Now, the CPU doesn't stop mid-instruction. That would be messy. It finishes the exact thing it's doing, and then it saves its place. It records the address of the very next instruction in something called the program counter. This is literally our chef putting a bookmark in the cookbook.
Next, with its place safely bookmarked, the CPU jumps to the memory address where that special interrupt service routine is waiting. It's no longer looking at the main recipe, it's now executing that mini recipe for handling the timer.
And once the ISR is finished, the CPU runs a special return command. This reloads that saved address right back into the program counter. And just like that, our chef picks up the cookbook, finds the bookmark, and resumes the main recipe seamlessly as if they were never disturbed. So, this all leads to a really good question. An oven timer is one kind of interruption, but a doorbell is completely different. How does the CPU know which mini recipe, which ISR to run for each different type of interrupt? Well, the solution is just brilliant. It's a clever bit of organization called the interrupt vector table. You can basically think of it as a lookup table, an index at the beginning of the cookbook. When the CPU gets an interrupt signal, it just looks up the interrupt's type in this table, and that table points it to the exact memory address for the correct ISR. It's simple, it's fast, and it's incredibly organized.
Okay, so we've seen all the mechanics, but let's zoom out for a second. Why is this so incredibly important? Well, because this isn't some obscure, low-level process. It's everything. The letters appearing as you type, that's interrupts. The cursor moving with your mouse, data arriving from your Wi-Fi, timers in your operating system, all of these everyday actions are managed by interrupts.
So the crucial takeaway is this. Interrupts
are the invisible engine that makes modern, responsive computing possible. They allow a single processor to efficiently juggle dozens of tasks, giving us the illusion of doing everything at once. It's not magic, it's just a very well-organized system of taps on the shoulder.
And that leaves us with one final thought. Just imagine a world without this elegant system. A world stuck with that constant, wasteful polling. Our computers would be slow, clunky, and barely able to do one thing at a time. It really makes you appreciate these unsung heroes working away inside our machines every single second.